Earth's magnetic field, also known as the geomagnetic field, is the magnetic field that extends from the Earth's interior out into space, where it interacts with the solar wind, a stream of charged particles emanating from the sun. In principle, we can detect the Earth's magnetic field all around the planet. In simple terms, the Earth has a north and a south pole, just like a small bar magnet. For this reason, the needle of a compass will point in a north-south direction, with the arrow pointing northwards. And this will happen anywhere on Earth apart from areas close to the poles. However, because opposite poles attract, the geographic north pole is actually the magnetic south pole, and vice versa. On closer examination, we find that magnetic field deviates slightly from the geographic north-south axis. At present, it tilts away from the Earth's rotational axis by about 11.5 degrees. To make navigation more accurate, maps usually show the small correction that needs to be made to take into account the local difference between magnetic and geographic north. The Earth's magnetic field is probably created by the movement of molten iron in the Earth's outer core. It protects our planet against the charged particle of the solar winds. Because the Earth's magnetic field is constantly changing, it can provide valuable information about a planet's formation. This is because for millions of years, and even today, volcanic activity in the planet's interior have been forcing molten rocks to the surface, where it cools and solidifies. As it starts to cool, however, any mineral in the still liquid rock that can be magnetized, such as magnetite for example, always align themselves with the magnetic field as it is at that time. When the rocks harden, those tiny magnets are locked permanently in position. After spending years studying changes in the magnetic field, scientists can now tell exactly when a particular sample of volcanic rock was formed. Magnetic fields are not made up of tangible matter. They are invisible and therefore cannot be observed directly. However, there are certain metals that respond to magnetic fields. As every school child knows, iron filling in the vicinity of a magnets form themselves into tight rows, linking the magnet's north pole to its south pole. These rows indicate how and where the magnetic fields run. The compass needle works on the same principle. The magnetic north pole of the compass needle always points exactly to the magnetic south pole of the Earth's magnetic field. With the help of sophisticated equipments, it is possible to determine the strength as well as the direction of the magnetic field.